Okay, so we've reached the point now where we're moving from the theory behind the sample mean of a population to actually the bit that's examined within the WJC course, which is hypothesis testing for this mean. So the context that we're using as we lead up to EG1 is to do with this newspaper reporter in a town called Avonford, who's met with a lab assistant who is taking CO2 samples within the town to check whether or not the CO2 levels within the town are within safe levels. So that's all condensed into this particular question. So Amy Williams, who was the reporter, believes that the CO2 level in Avonford has risen above the usual level of 328 parts per million. A sample of 10 specimens of Avonford air are collected and the carbon dioxide level within them is determined. The results are as follows. So those are the 10 measures that were sampled. Extensive previous research has shown that the standard deviation of the levels within such samples is 2.5. Use these data to test at the 0.1% significance level Anna's belief that the level of CO2 at Avonford is above normal. So before we got to this first example, we'd already worked out what the mean of those temperatures are, and it worked out to be 331 parts per million. So we'll bring that through from the previous work. Right, so you've met hypothesis testing before at AS, and in AS the hypothesis tests were based upon binomial distributions. In A2 it's to do with the normal distribution, and we're looking at the sample means. It doesn't have to be uniquely sample means. You could work with different measures that you've sampled, but it's the mean that is the most commonly used within statistics. So in the same way that you would have set this up in AS, we'll work through our null and alternative hypotheses and then look at the two different methods of testing those hypotheses. So first of all, within the context of this, our parent population is going to be, if we define it as X is the random variable parts of CO2 per million in a sample specimen, sorry. So that's a random variable. Then X is going to be normally distributed, and it's going to have a normal distribution with, for the parent population, a mean of 328 per million and a standard deviation of 2.5, which we write because within that bracket it's variance, so 2.5 squared. So that's our parent population. Then our sample population of means is going to be capital X bar, and then this will also have the same mean as the parent population, so 328, but the standard deviation is reduced by the factor of the square root of the population size, sorry, the sample size. So in this case that would be 2.5 over 10 as a variance. So the standard deviation, just to make that clear, in this case that's the variance, which means the standard deviation is 2.5 over the root, square root of the sample size, which is 10. So that's the standard deviation that we're going to be working with, but it's written as variance. Okay, and our calculated sample mean is 331, and that's lowercase x bar the sample that the lab rat took has got a mean of 331 parts per million. Right, then we come to the hypothesis test. So just as in AS, we start off with our null hypothesis. And our null hypothesis is the status quo. The null hypothesis, which we use H with a sub-zero to represent it, the null hypothesis in this case is that the mean is the same as the parent population. So the mean is 328. So to turn that into a context, what we're saying there is the level of CO2, should be a little 2, shouldn't it? The level of CO2 in Avonford is normal, where normal is the usual level of 328 parts per million. Our alternative hypothesis, which is what AMA is pursuing, is that the level of CO2 at Avonford is above normal. So the alternative hypothesis, which has got notation H1, is that the mean is going to be greater than 328. And in the context of that, that means that the level of CO2 in Avonford is above normal. Sorry, and that should be lowercase n. It's not the normal distribution, it's just above normal values, typical values. So that's setting up our test. We've identified the normal distribution of the parent population, defined the random variable. Then we've taken our sample population of means, which is going to have the same mean, which we looked at with the central limit theorem in the build-up to this example. And then also part of that central limit theorem is the fact that the standard deviation of the sample is going to be the standard deviation of the population divided by the square root of the number of items in your sample. Then we come to carrying out the test, and hopefully what you will remember from AS is that there are two different ways to deal with the hypothesis test. Method 1 is you calculate the p-value. I'll talk more about that in a moment. And then method 2 is you find the critical region. So if we consider what we have here as a normal distribution, the mean is 328. And with the p-value, what we're interested in doing, and the significance level here, which I hadn't mentioned up here, which I should have put in, let's squeeze it in there. This is going to be a one-tail test because the hypothesis we're testing is clearly dictating one outcome we're interested in. In this case, that the level of CO2 is above normal. Could have been one-tailed test where it was below normal, in which case the mean inequality there would have been mu less than 328, or as we'll see in later examples, it could be a two-tailed test where we would just be saying that the belief that the CO2 level in Avonford is different, but not specifying whether it was higher or lower. So this is a one-tailed test, and it's at a really narrow level of significance, 0.1% significance. So coming back to the p-value, what we're working with the p-value is we want to find out with our sample mean, which is 331, what the probability is of that occurring by chance as opposed to occurring outside the parent population. So what we're working out is this area here, the probability that the mean is greater than 331. If that is really, really small, and by really, really small, I mean if that is less than the significance level, which in this case is going to be 0.01, then it's significant, and that gives us cause to reject the null hypothesis. So if we're working with the p-value, we are calculating the area. So the p-value equals the probability that x bar is greater than our sample mean. So on our calculator, we're going to go menu, 7 for normal distribution, 2 for the cumulative distribution, the lower value 331, the upper value 1 times 10 to the 99. The standard deviation is going to be 2.5 over root 10, which we can just type in like that. The mean is 328. So that works out to be a probability of 7.39 times 10 to the minus 5, which is 0.00001234739, which is smaller than our significance level. So since p-value is less than our significance level of 0.1%, we say that the null hypothesis is rejected. So I'll come to the final part of the language in our solution in a moment, but let's flip over to method 2, which is finding the critical region. So what we do here is the reverse of doing this. What we look at here is, okay, if we've got a significance level of 0.001, what mean value produces that area? And then if our calculated mean of 331 is beyond that, it puts it within the critical region, therefore it corroborates what we did this method in that we can reject the null hypothesis. So the other method is going the other way, where what we want to work out is what that is there. So on our calculator now, back to the normal distribution, but this time we're going to go backwards, so it's the inverse normal. We're interested in the area of 0.001. It's pulled the standard deviation and mean through that we were using in method 1, so I don't have to re-enter those, and I can see that that gives me a calculated mean there of 325. Oops, no, hold on, slipped up there. In that, because this is a less than, it's not that I'm going to be putting into my calculator, it's this region, which is 0.999. Now the reason I suddenly stopped there and said hang on, that doesn't seem right, is because 325 is to the left of the mean, so immediately I can see, oh hang on, I made a mistake there, what have I done? It's measuring less than. So I want to go back in here, 3 inverse normal, and I want to put the area in of 0.999, which then gives me a calculated value of 330.44. So the critical region will have the mean greater than 330.44. Our calculated sample mean is 331, which takes us into that red zone. So the sample mean x bar lies within this critical region, so therefore the null hypothesis is rejected. So we arrived at the same conclusion in 2 different ways. One way, working with a given calculated mean to work out the associated area, or working out the area given by the significance level and working out whether our calculated mean lies within that critical region. The last thing you have to do is to then bring this into a conclusion in the context of the question. So we're saying that the null hypothesis is rejected. Excuse me, what we never then do is to say this proves that the CO2 level is above normal. It doesn't prove it, it just implies that there is some evidence to suggest that that is the case. So the final bit is to say there is some evidence to suggest that CO2 levels in Avonford are above normal. And I'm not going to repeat it over there, because once you've chosen your method, then you're only going to conclude once. So those are 2 methods. You need to be comfortable with both, because there's no reason why a question can't demand which method they want you to use. So although you may instinctively feel one method is more straightforward than another and want to use that more frequently, that's fine, but when it comes to getting prepared for an exam, you need to make sure that you can deal competently with both directions in case they push you that way.